talking about the knowledge separation and diffusion models for text generation.
Thank you, Simon. Okay, hi, everyone. Thanks for coming here so early. I really appreciate it. My original title was Latent Diffusion for Text, but actually we just worked on a paper for Cornell. Actually, Colum, how do you say it? Colum. Last Friday, and on the plane I got so excited, so I actually made some slides for this new project. So I also thought there's some smart people here in the room, so I would love to share and hear your opinion. So the first topic is large memory language models, LM. My students insist it's called LIM. And the main goal is about separating knowledge from language. And so to illustrate this, let me tell you some facts about Napoleon. So here are two factual sentences about Napoleon. This is a Gemini image of Napoleon and his mom. The first sentence is, Napoleon had a mother who gave birth to him somewhere, right? And this is a completely factual sentence, right? Contains a whole bunch of facts, right? He had a mother, right? She gave birth to him, right? These are all facts, all correct. And I claim, everybody in this room could have produced this sentence, right? If I'd asked you generate a sentence about Napoleon that is absolutely true, right? You could have definitely come up with this sentence, right? Whereas here's the second sentence. Napoleon was born on August 15th, 1769, in, I don't know how to pronounce this, whatever, Corsica, to his mother, Laetitia Bonaparte, right? This is a sentence that's much, much harder to produce, right? And I claim that, I don't know, maybe raise your hand if you think you could have produced that sentence, right? Probably hardly anyone, right? And so the difference is both of these are factual, right? Both of these are absolutely correct. But what I claim is that the first one only contains common knowledge, right? Like Napoleon had a mother, duh, right? And so on. She gave birth to him. Well, that's what mothers do, and so on, right? On the other hand, this one down here contains knowledge that's very, very specific, right? He was born on August 15th, 1769. And I call this tail knowledge, right? And this here common knowledge. The idea basically is there's a heavy tail of knowledge, right? And there's some knowledge that everybody knows, right? Even if you're an 8-year-old kid, you know that everybody has a mother, right? And there's this tail knowledge that only very, very few people know, right? If I were to find a random person, right, it would be very, very unlikely to find someone that actually knows all of these things, right? I'm sure someone at Berkeley knows this, right? But it's very, very rare. And I claim this is the main problem that LLMs have right now, right? That basically we're trying to cram all of this into our model weights in some distributed form. So our LLMs basically learn three things. The first thing is language competency, right? They learn how to talk, right? How do you speak? What are the rules, grammatical rules of the English language or French language, and so on, whatever, right? How do you produce, fluent language? That's very important. I think we all agree that that's kind of the big deal of LLMs. Then we have common knowledge, right? I claim for that you don't need a whole lot of data, right? Like, Napoleon had a mother, right? It's very simple. And then we have this tail knowledge. And the tail knowledge is why we need so much data, because these are very, very specific things, right, that we have to drill in. And this is the root of all evil, right, in some sense. We need huge models to store all of these things, right? These are not compressible. Right? If you think about how many bits you would need for this sentence, right, this sentence here is not very, very surprising, right? Like you could compress this in a couple of bits. Whereas this here is extremely surprising, right? You have no idea what the state is. So you need many, many bits for this, right? So you need a lot of capacity to store these things. And this is also where hallucination comes from, right? If you don't know a specific fact, right, the language model doesn't know if it knows something or doesn't know something, so it starts saying something, right? So the goal of this project, of this, what I'm trying to convince you in this talk, is to separate this, right? I claim that these two things should be stored in the language model, in the weights. I think this is good, right? Whereas the factual tail knowledge should be stored in a database, right? This really doesn't belong to the model weights. And if we do this, then we can actually make this model much, much, much smaller, right? And much faster to train and cheaper to operate, right? And on the other hand, we are no longer limited by the model weights for the tail knowledge. So we can make this external database really, really big, right? We can make it editable. We can interpret it. Right? We can look at it, right? So for example, let's say the president of the United States, right? The common knowledge is the United States as the president, right? But in the database would be who the president is. If the president changes, we just change the database, right? We don't have to retrain the model, right? And finally, you can also ground all these facts. Right? Every single fact that's in my database, I can link to the source where it came from. So when you actually then generate the text, I can make a link that actually people can verify this is factual, or this is still the case. Right? So my claim, this is a workshop on the future of LLMs. I claim this is the future of LLMs. Right? We have to separate these two. Right? Actually, my prediction is in a couple of years, people are going to look back and think it's crazy to cram all of this into the model weights. OK, so I thought about how can we do this. And my students and I started working on this. And what I'm trying to convince you is that there's a very, very simple trick to do this. And actually, that you can do with any language model. You don't even have to change the code. You don't have to change the architecture. You just change the way it's trained. And the trick is a pre-training trick. So you have to do this during pre-training. And essentially what we're doing is just changing the data. Right? So if in the database, for example, in our pre-training corpus, by the way, interrupt me at any time if you have any questions. Yeah?
Just because there exist these two cases that are easily separable, I would argue that like most stuff is not.
Good, good. So the question is, what is in between, right? So there's tail knowledge, there's common knowledge, right? And there's stuff that kind of falls in between, right? But some people, it's a power law distribution, right? And I think that's right. There's, for example, I may be into soccer. A lot of soccer players know, whatever, who Haaland is, right? Is the star, player in Man City. But people in the United States may actually not know this, right? So it's kind of it's fuzzy in between. I think that's fine. We actually let the training process decide where things go, and so we don't have to specify this. Okay, good. Very, very good point. Very good point. OK, so here's what we do during training. We essentially change our training data. Let's say this here is this is the sentence that we just had. Napoleon was born August 15th and to his mother, Letizia Bonaparte. Right? And so here I kind of separated in blue what I think is common knowledge, and in green what I think is tail knowledge. Right? But again, here I'm drawing a hard boundary, but it doesn't have to be that hard. And essentially what we're doing is we are changing this into the following sentence, where we basically say Napoleon was born on, and then this term here, we assume the language model doesn't know, but can look it up. So we basically have a special token that says look up in the database, and then we say Napoleon birth date. So we basically have an entity and an attribute, and then we pretend, right? We pretend there's a database. This is all just fake, right? We're just making this data set up. So we say, this here is the output of the database call, August 15th. And then we actually continue with our text. Sorry, this should be 1769. This is missing here. There's a typo. It should have 1769. Same thing again, the birthplace. Instead of saying just the town where it's born, we actually put in a special token saying Napoleon birthplace. And then we basically insert the answer that the database should give us. And then we continue with our text. Does that make sense? Any questions about this? So you're basically annotating the text with fake database calls to a database that doesn't exist, right? But we basically pretend, essentially whenever you don't know something, we just teach the language model, you can just look it up, and you look it up, and then here's the answer, and then you keep talking, right? Conditional on the fact that you just saw the answer, right? Does that make sense? Any questions? Yeah.
Common knowledge you mentioned, it's true that everyone can come up with it, but it's kind of like smart. I don't think the model actually do that. For example, they might actually come up with some hallucination. If you ask for a random person that when he is born, you can come up with some random date which is not meaningful, instead of saying they born on some day of the year.
Now, all you need to know is that the person was born, right? So I want to talk about Sasha, and I say, where was Sasha? When was Sasha born? I just say Sasha was born in, and then I, look up when he was born, right? So the idea is I'm training the language model to never actually say facts on its own right, but to always look them up. That's the trick, right? So the language model basically learns that it doesn't know anything. That's the whole point, right? It's like kids with an iPhone. It's like you just look up everything. So that's basically how we change the training data. Whenever there's any fact, we just insert a fake database lookup in here, right? But it's similar to the tool format paper, where you basically here in this case we look up the birth date of Napoleon, and then we get the result. But we pretend to get the result, and then we actually continue. Does that make sense? Any more questions? Yeah.
Yeah, I'm wondering if you can scale this to like internet scale kind of data, because you want to do this for pre-training, right?
Yeah.
So it seems that annotating or changing the data to these kind
I'll show you how to do it in a minute.
Okay.
Good. All right, good. So, one more time, so all the common knowledge turns into lookup keys. We use our common knowledge to look things up. Then tail knowledge, essentially we get, database return values, and tail knowledge is nothing we know. We just copy it from the database. We just copy it from the return value. So here's the return value, and then we copy it. So we train the language model, look things up, and then copy from the answer. Right? That's the idea. Okay, so now your question, how do we do this on a large scale? And essentially, so we did it on Wikipedia. So this is our, all our examples are just limited to Wikipedia. But, essentially what we do is we just, generate a prompt for GPT-4 to go through the text and change the text in exactly this way. So you basically tell it to extract all factual entities, right, and create these, fake database lookups, right here. Then this data set, the data that we then have is basically usually kind of rough. Then we have a second GPT-4 pass that actually corrects it. So essentially it goes through, corrects, makes sure the keys kind of sound similar. Right? There's no references to the future in the document. Like sometimes you look something up that you only need later on. Basically it uses knowledge from later on to actually find the database keys. That's not allowed. So this, basically rewrites the text to make it all correct. And then we do this to generate a small seed data set. And then we take a small llama model that we fine tune on this data. And that model is small enough that we can run it over a large corpus. So that's kind of, the answer to your question. So now we can just go over all of Wikipedia. It took us, less than a day, like a couple hours, like 12 hours or something, to process all of Wikipedia and change it all into this format. Any questions? All right. How do we create the database? Well, once we have the data in this format, we can just take all these triplets and turn them into database entries. So here we have Napoleon, birth date, and it links to August 15th, 1769, right, and so on. And we see how this works, right? So in some sense, once the data is processed, building the database is trivial. Right? We just go through it and do it in one pass, right? That's easy. And how do we train the model? We just take this corpus and we just do next word prediction, just like a normal pre-training. Only one difference: we don't backprop on the return values of the database, right? So basically, we say, here we predict the next word, predict the next word, predict the next word. So we teach the model to put in here the lookup table, a lookup call. Then we teach it to come up with this key and the attribute. Then we don't teach it to come up with this because that actually comes from the database. And then given this, we actually teach it to copy the result into the text. All right, does that make sense? Any questions? Yeah.
How do you handle the problem that the fact may be referred to through some reasoning? Like I can say the French emperor in the second half of 18th century was born on this day.
I see. It doesn't work on everything, right? It's not that it, but the model. The point is basically you reduce the model a lot. Like it's not that it knows. It can still do reasoning, right? And maybe. So in some sense, what the corrector does, it also changes the text, the training text, to be consistent with this. So there are certain texts where it doesn't work as well. Okay. And then doing inference, what we do, well, you can, it's obvious at this point, right? You just generate something Napoleon was born on. It generates this lookup table. Here at this point, we actually do call the database. We inject the output. And then actually it says August 15, 1769, right? Yeah. Yeah.
So you said you don't do backdrop on the red portion, but you do it on the green portion.
Yeah.
How do you control that the model will learn to copy the previous text and not actually store it?
Yeah, that's right. It's a good question. So the question basically is, here we do backprop on these tokens here. How can we avoid that the model actually learns it, right? And I guess it's just so much easier to copy it than to actually memorize something, right? Like to memorize, these are extremely high, low entropy tokens, right? So this takes a lot of bits to compress this. But if you just copy it, it's actually super easy to do. And so in practice, the language model just does it. It may learn a little bit of facts, right? But we have an experiment later on where we just force it to, to actually, basically what we do during inference, we actually just switch off this call. So whenever it tries to do a database call, we just forbid it. We just remove that token. And so it actually has to kind of do stuff on memory, and it completely tanks. Right? It gets really, really bad. Right? So we know that it actually hasn't retained the memory. Very good point, though. Very good point. Yeah, question.
That bug does not exist in the database at inference.
Very, very good point. Very good point. So what if we call something and actually Napoleon birth date is not there? There's two reasons for this. Right? Either because we actually don't have it at all, or because we say something else. We say birthday instead of birth date. Right? Here. Key mismatch problem. So we came up with two solutions for this. The first one is a fuzzy lookup. So essentially what we're doing is, similar to actually all the work from Seon, we basically just embed this, if there's no exact key match, we basically embed this key and then look up the most similar key in the database, right? That's the fuzzy lookup. The second thing is during decoding, we have a prefix tree that basically says, the moment you say Napoleon, you can actually only say the following things, right? Like you can just force the decoding to only say valid keys, right? Both of them work. This is a lot faster, leads to a lot less memory because you don't have to, here you have to pre-compute all the embeddings. So this one is a little better, but it's slower and needs more memory, and this here is faster and slightly lower accuracy. Okay, the other thing is here, what's nice actually is if there's nothing close by, that's the second case where a key may be missing. If there's just no close key, then we can just return unknown. And then actually, the language model basically can just say, I don't know. Right? Yeah?
So earlier you showed that you do basically labeling in the beginning for Wikipedia. Why can't you do that after inference? So you have a response, and then you ask, like, what are the facts you can find it about the response, and then you find the Napoleon name, and then you look up in the database the fact. So what you're doing, but instead of pre-training, do it.
I see. Right. That turns more into RAG. Yeah. So there's kind of a fuzzy boundary between this and RAG, right? So our goal is much more to really remove knowledge from the language model, to keep it small and lean, that we need less data and can train it faster, right? And then we can edit all the knowledge later on, right?
Well, you remove it anyway because you just see the word Napoleon and then use RAG to find all the facts related to Napoleon and then the relevant one to back in.
Yeah, but the model will still know a lot of stuff, right? You still need a huge model, right, that you're training. So
no, it just needs Napoleon.
I understand. But I'm trying to make sure that the model can be much, much smaller than it is, right? So in some sense, this is kind of a pre-training technique, right, to remove knowledge from the model. You wouldn't remove any knowledge from the model.
So suppose we have your small model, but we don't have the added birthday date, right? So then you have the small model, and then in response it says Napoleon, so use a small model.
So you could still use this with RAG, I guess, if you want to. Absolutely. Right? You could still actually, for example, you could give it all the keys that Napoleon has, etc. Right? There's many directions you can go from this. I totally agree. Okay. Yeah. Okay, good. So just to show you some results. So here's actually this is an GPT-2 model, 124 million parameters, so it's relatively small. We trained it on wiki corpus, and this here is standard pre-training, the perplexity as it goes down as we are training. And this here is, if you do pre-training. And what you can see is there's a huge drop in perplexity. So, and this is actually not too surprising, right? It makes a lot of sense because, the tokens that it says all make a lot of sense. Napoleon was born in Napoleon birth date, right? Look up, right? So it always it's much, much simpler language, right? It doesn't actually remember any facts, right? There's nothing surprising anymore, right? So, but it basically helps you to kind of, if you have a small, you can have a smaller model and you can learn much faster, right? Which is what we're hoping for. We can train it on, this is a fact score. It's a data set where you basically generate biographies of people. And so this is here, tell me a bio of Kang Shi-wan. I don't know who that is, but my student says he's very handsome. And then it starts generating some biography, and it's checked for factual accuracy. This the way the data set works. And if you now look at this, so this here is standard pre-training. This is a GPT-2 model standard pre-training. And this gives us, 10% accuracy. This is a very small model, so larger models would have larger accuracy. But, if you use our pre-training instead, you actually double the accuracy on the fact score. This term up here is if you take the original GPT-2 model, which was trained on a much, much, much larger corpus. Right? So here we are trained only on our data set, so we kind of drop it. But then actually, once we use our pre-training, actually, it goes way up. Same thing here on a Llama model. This is again a small Llama model because we are compute constrained. But again, it more than doubles. Right? The fact score more than doubles the moment we use our pre-training technique, right, over standard pre-training. Yeah.
In your work, you're trying to, from the beginning, the language model should not be predicting facts. Right?
Tail facts, yeah. Uh-huh.
Facts. How would it compare with equally small model, but paired with a retriever, and then further fine-tuned such that it always has a context to look up to and then predict?
Yeah, so we don't have those results yet. This is the problem when you present results that this is only 3 days old. So it's an obvious thing we should compare against. I agree, right? But it's a little, what claim is a little different because the goal here really is to have these very, very simple models. I guess if you have exactly the same size model,
also,
and you have a retriever.
Like with retrieval, we are going more schema-free. Here it's still like a database with sets.
So that's, I'll let you know soon. Here's another fact data set. Again, we see the same thing, that basically it doubles in accuracy and in factuality. One question is, does it hurt natural language understanding? So we have a bunch of data sets. Don't think I included them. These are standard data sets on natural language understanding. And what you can see is, basically this is again the same thing. We double this. The y-axis here is the fact score, and the x-axis is the natural language understanding performance. And what you can see is here GPT-2. When we switch to our model, our pre-training, the factuality doubles, but actually the natural language performance does not go down in any way, right? In fact, it improves ever so slightly, right? Same thing with Llama, right? It goes a little bit to the right, but actually the factuality goes way up, right? So this line here. So basically, it doesn't hurt its language competency. Yeah.
So one question might be that it maybe gets better at this thing, but is it reusing its other capacity for other aspects? Was that the kind of goal that
it's a good question. So would it get better at other things? So we haven't seen that it gets a little bit better here at language understanding, right? It mostly just gets a lot better at factuality. So it's a good question. What if you could hammer in more stuff, if you train it for longer or something. I
guess the theory of the case is that it's not wasting capacity on memorization. So you hope that capacity goes to other things. Is that what you're saying?
That is true, and in some sense, it performs as good as a much, much, much larger model, right? On factuality, right? Like it basically learns how to generate these keys, right? And that's much, much easier. It can learn to generate a lot more keys than actual factual knowledge.
But so, even with other non-parametric methods, we see fact scores go up, right? So it gets a lot just from having the database.
Yeah, that's true. That's true.
The novel thing here is that it doesn't have to store that.
Yeah. I think what you're really saying is we really have to compare against RAG. And
no, I'm saying the opposite. What would you want it to use the non-RAG capacity for, right?
Well, what I'm hoping is that it basically gets really good at generating keys. That it basically uses all its capacity just to generate keys to look up things.
Okay.
Right? Yeah.
You know what would happen? I think this method really fits to Wikipedia data because it has also facts. What would happen, for example, in math problems?
It's a good question. So the question is, I don't know if I have to repeat the question. So the question is, this is great for Wikipedia because it's very factual. What if this is, applied to math problems? We haven't done that yet.
Logical inference, for example.
Right. My assumption would be that it's probably just there's probably maybe no difference to another model because you don't actually use facts very much.
I mean, I would want it to call the database to get some sentences, like math sentences, but to make the logical inference by itself, for example.
I'm sure there's a way to extend this to these scenarios, right? We haven't gone there yet. I think it's an interesting direction of future research. Yeah.
Yeah. So this is probably great for perplexity, that as you shown. But most tasks, when you train it for natural language understanding, you're kind of pushing the model to out of distribution, because during training, you have never seen, like during language modeling training, it always sees the database triples that you have. But if you show an new task, you will have some input and you're trying to predict some output. So in some sense, like this feels to me very out of distribution based.
Yeah. So basically, right, so the question basically is when you do these NLU tasks, you're actually not using database lookups, right?
You're not using database lookups, but you're also not really. The reason why we use language models is that the representations that these models build will transfer to all sorts of natural settings. Those settings also look similar in some sense.
Right, so these are actually a whole array. This is the average performance across many different tasks. It's a whole benchmark suite. And so in these, basically, you're totally right? It doesn't use the database lookup, right? Because these actually don't require you to do any factual memorization.
It also doesn't look like language, like the
yes, like multiple choice questions and so on, right? Now, like basically you have to get a little text and you have to do comprehension questions, right? The important thing is that basically you're not getting worse, right? So basically, or you're getting slightly better, I guess, because we have a little bit capacity freed up, right? So I guess what my point is really that these are orthogonal, right? Language understanding is one direction, right? And memorizing tail facts is an orthogonal direction, right? And we are basically squeezing out these tail facts, but we are still just as good in the memory, in the language understanding.
Did you try any mixing experiments where you also, during language modeling training, where you put natural data instead of putting triples, like what you do?
No. Okay, good. This is actually the end of my first half here. So basically, I guess what I hopefully convinced you of is that there's this very, very simple trick that we call lim-lim. And it's basically a pre-training method, and that separates tail knowledge and common knowledge. And I think it has a lot of potential because it, basically automatically creates this database which solves a lot of the problems that we have currently with language models. Right? We've only started. This is basically the very first work on this, but we haven't evaluated this, how this affects hallucinations and all this stuff, right? And fact editing and so on, right? Also with a very, very small model, they can then perform, the same accuracy levels as a much, much bigger model. Okay. If there's no question, then I'm going to switch to the second part of the talk, which was actually the talk that I'm supposed to do, which is latent diffusion. So, yeah, you have a question? Okay.
Sorry. Maybe it's because I missed part of the initial part of the talk, but you showed that the memory is editable, but I didn't see any results showing that if you edit this knowledge base, because I think a question earlier was investigating when you backpropagate, how do you make sure, how are you certain that it isn't actually just incorporating this into parametric knowledge?
Mm-hmm.
But have you tried doing anything where you're sort of corrupting the database?
Yes, we have. So I don't have this here. Yeah. But basically what we did is we forced it that doing inference, basically, that whenever I did a database lookup, we just didn't allow that token. So it couldn't do database lookups anymore. And so it had to remember everything from parametric knowledge. And the performance completely tanked.
But what if you change the database?
So we haven't done that yet.
Yeah, because I think it could be interesting also to see if it's something completely different, like all of a sudden you look up Napoleon's.
Yeah, it's definitely on our to-do list. Okay. So we submitted this to Column, and then my students literally finished this at the airport actually, and then they all went to Puerto Rico and partying there right now because we have spring break. Once they're back, this will happen. The paper's not even archived yet, so it's this is very, very early stuff. But yes, absolutely. It's in the pipeline. Okay, any more questions? Okay, good. Latent diffusion. So this is actually what Sasha asked me to talk about. So it's it's a different topic, but it's actually related. I don't have to convince you that LLMs are amazing, especially not at this workshop. But my claim is that they're actually hard to control. Right? That basically we all know read these cases in the news where bot suddenly says something crazy, Diffusion models are also amazing, and they're really easy to control, right? So in fact, the news was the other way around, right? So Google actually kind of over-controlled, some of the, I think it got, some of the images and created a female black pope or something, and ended up in the New York Times. But the point here is really, the fact that this is so easy to generate, right, is actually a feature of diffusion models. Now here's the question. I have a 3-minute introduction to diffusion models. I don't know if people want me to do this or not do this. So do a thumbs up if you want me to do this. Thumbs down if not. Okay, I see 1 thumbs down and 50 thumbs up. Okay, good. So you got outvoted. Okay, so when I teach diffusion models, it takes me, a whole week, and I go through all the gory math. So this is actually a 3-minute version without any math, hardly any math. Obviously, it means something is left out, but so on the high-level picture, diffusion models are very, very simple, right? So you want to generate an image, and so you don't know the distribution of images. That's very hard to get to. We have images. These are sampled from this distribution. We don't know what the distribution is. We can't sample from it. But we can sample from a Gaussian distribution. So what we do is we just sample Gaussian noise in the shape of an image, and we map that onto the distribution of images, onto the manifold of images. That's the idea. That's the high-level goal. And you can just sample new noise, and you get a different image, and so on. How do you do this? And at the core of this for images, and I'm going to go to text in a minute, is the UNet. Right? UNet initially invented for cell segmentation. It's an image translation network. So you put an image, and then you have ConvNet that maps it into this latent space, and then maps it blah blah. And then here you actually have some task, and you basically have paired data. This is my input. This is my output, and you just train this such that the output, from this image I get my output. You just do the square laws. Feel free to ask me questions anytime. So one thing you can do with a UNet, you can train it to denoise. So this here is an image. Does anyone know who this is? Yeah, Carl Friedrich Gauss, right? So we add Gaussian noise to Carl Friedrich Gauss. He had it coming, right? And then we train the network to denoise it, right? So this is a very easy task, right? We can actually get infinite amount of data from the internet, or almost infinite amount of data, and we can take all these images and just add random amount of noise, and then just stick that in, and then we want to get the original image back, right? So we have pairwise training data as much as we want. Just train this unit. And we vary the amount of noise, from 0 to 1. This here is a lot more noise. The other thing is we only one complication. We tell the neural network how much noise we added. Right? That's kind of give it a little hint. And usually you put that into the norm, into the batch norm or something. So one more time, the input is a noisy image and the amount of noise that I added, and the output is the denoised image. Okay, this makes sense. This should be relatively easy to train. Now comes one more twist. I can actually give it a description. An oil painting of an old white man with a white shirt, blah, 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 right? And if I have such a description, I can embed that as vectors, as text vectors, and I can do cross-attention. And that actually helps that even more, right? So if I have a noisy image here, but I tell you it's a painting of an old man, right? And this is not a pancake, but it's probably a face, right? And you can denoise this better, right? So this additional information helps you with this task. Okay, any questions at this point? So this, what I'm trying to convince you here, that training such a denoising network is actually really easy, right? It's just a few lines of PyTorch, right? And the data set you get for free from the internet, right? Because once you have this, you actually can do diffusion models, right? And essentially what a diffusion, denoising diffusion process is you just start with a description, an astronaut riding a horse, and I just sample noise, and I basically pretend that I took this image of an astronaut riding a horse, and I added so much noise to it that you can't see it anymore. In reality, I didn't do that. In reality, I just sampled noise, right? And I stick this through my denoising network, and I tell the network, okay, this is an astronaut riding a horse, right? Please remove the noise, right? And it tries the best it can do, right? It gives me some blurry version of this asset, because it doesn't know, right? But then what I do is I just take this blurry version of denoised image, and I add noise back in. Just a little bit less noise. So I take the denoised version and I add a little bit of noise. And then I run it through the denoising again. And I get this version and I add a little bit of less noise to it, and I denoise it again. and I add a little bit less noise to it, and I denoise it again. And slowly you realize that this blob here, right, turns into a horse, right, because I told it it's a horse, right? And I keep doing this, and eventually I'm getting an astronaut riding a horse, right? And so this here is just my unit that I just trained, right? So all I need is one network that can can take a noisy image and remove the noise, right? And then I just apply this over and over again, right? Start with noise, denoise, add noise back in, denoise, add noise back in, and so on. And you always add a little bit less noise so that you slowly get into this final image. Any questions? Make sense? So it's really simple, right? That's the beauty of diffusion models, right? If you have sample noise, different noise, here I sampled 3 times different noise. Actually, it's taken from this paper. You actually get, different astronauts riding different horses, right? Initially, it all looks very similar, but then, just small changes, lead to very different final outcomes. That's the idea, right? So the beauty of diffusion models really is they're so simple, right? And, very robust, right? Not as unstable as GANs and so on. That's why we all love them. Now, one thing that's really, really cool about diffusion models is they're very easy to control. And so imagine here I'm starting with my noisy image, and I denoise it. Here's the denoised version as it changes over time. Let's say I want it to be a brown horse, right? Then what I can do is I can just take a classifier, a brown horse classifier, right? And these classifiers are easy to train because I don't need much data for it. And then, what I do is when I denoise, so this here was the step that I always had. I take my image xt, I denoise it, then I add noise back in, and here I'm adding a little bit in the direction of brown horses. So this classifier basically tells me where are brown horses and where are not brown horses. Right? This is this is just some hyperplane. So this gives me a direction, saying if I'm here, I have brown horses. Right? This could be anything. Could also be whatever, like male astronauts versus female astronauts or something, right? Or that doesn't matter. This classifier just gives me a direction, and I can just add this gradient basically to my noise. And if I do this, there's a cartoon image, but basically it shifts the denoising process in this direction. Right? This is the idea. This looks like a hack, but it's actually if you do the math, this comes out very, very nicely from the score model view of diffusion models. This is, but there's a lot of math. In the end, the rule is very, very simple. It's just this. Right? You just take the gradient of a classifier and move in that direction. So this is how you can do sampling. P of p. This actually I'm sampling p of x given y, right? But I just need a classifier y given x. Okay, good. So we want to use diffusion models for text, right? So for images, it's clear, right? We take an image, we add noise. We can, now we have these images and we have these noisy images and we denoise them. So this is easy. For text, not so easy, right? We have text. These are discrete tokens. How do you add Gaussian noise to that? Not so clear, right? So bunch of people have worked on this, and some people went down the route of actually having non-Gaussian noise. Basically, you just take this. Actually, Sasha has written a great paper on this. But you basically just mask out words randomly, and then you demask it. We're going to go down a different route. And what we're going to do is, this last intro slide, oh my gosh, is we're going to do latent diffusion, so in the latent space. So latent diffusion is a concept that's already been around in computer vision. And actually, whenever someone talks about diffusion models, they're probably talking about latent diffusion. Latent diffusion is how you use diffusion in computer vision. And the trick is very simple. If you basically, you train one more thing, it's actually an autoencoder. So an autoencoder takes an image as input and tries to decode the original image. You have no skip connections here. So I take this image, I map it into this latent space, and then I recover it. Right? This is an autoencoder. And I can train an autoencoder on unlimited amount of data. Right? I can just take millions of images from the internet, and I train it, take an image in, get a latent code, and then I decode it, and I'm supposed to get the image back. Right? And I do a square loss, and then propagate the loss back. So what an autoencoder gives me is essentially this latent distribution, which is really a compressed version of the image. Right? It's like, think of JPEG. Right? So this is much, much, much smaller than my original image. But if I have this, I can always take my decoder and get the original image back. Right? Does that make sense? So it's really just, instead of pixels, I have this code here. Right? And this code basically has the same information as the pixels. Right? Because pixels are extremely redundant. Right? Most neighboring pixels are identical. Right? Just look at the wall behind me. Right? So you can compress this like crazy. OK, any questions? So latent diffusion essentially just does the whole diffusion process not in pixel space, but in this latent space. That's the idea. Right? Because when you remember when we did this, added all this noise, started with an image, added noise, and then denoised it, added noise back in, denoised it. We did this in the image space, but really there was nothing specific about pixels. You can also do it in the latent space, right? So we basically take the coordinate, the dimensions of the latent space, we denoise it, add noise back in, and so on. And at the end, finally, we get some latent code. And if we put this in the decoder, we get our astronaut riding a horse. Right? So there's nothing, in some sense, you're basically, I'm just doing my diffusion not in pixels, but in this compressed representation. And the people who invented this, from the LMU in Munich, they just did this because they couldn't afford running, diffusion in pixel space. It's too expensive. Right? So this is much, much, much faster because you're doing everything in the compressed space. But this gives us an opening. Right? It gives us an opening because this latent space is continuous. Right? And so, one more time, let me just explain this. So how do you do this during inference? You basically sample some noise in the dimension of the latent space. You denoise it. You add noise, denoise it. This little arrow here means you go back and forth, get until you actually have this denoised completely. And then you stick it to the image decoder, and now you have your image. Right? So this here is the, you decompress the image, basically. Right? And the idea is you can do the same thing for text. Right? I can basically take some image noise. I denoise it until I get a latent code for my text, and then I put this to the decoder, and now I get this text here. The old clock on the wall ticked, blah, blah, blah. Right? So now I can use diffusion models for text. I don't have the problem anymore that I can't add Gaussian noise to text, right? Because I'm doing everything in this latent space. In the latent space, this is just real numbers, so I can actually add Gaussian noise to the latent space. Right? That's the trick. That's the solution to this problem. Any questions? Make sense? Good to move on. So what we need for this is an encoder that basically goes from text to the latent space and then decodes it again. There is a problem. The problem is the following, that short text has short code and long text has long code. So in images, that's not the case. In images, you always have the same size code. Here, because it's sequential, you actually have kind of one vector for each token. So we have to get around this. And so I'm not going to go into the details here. Well, the trick in some sense is to, here, I'm going to skip some stuff because we're out of time. But the basic learner compressor that actually compresses everything in a fixed size number of tokens. So no matter how long the text is, you always compress it into the same number of tokens. And the way we do this is through cross-attention. So we basically first encode it into a long sequence, and then we do cross-attention over here from our latents. And, details. But ultimately, what we can do is we can take any text, compress it into a fixed size code, and decompress it again. Yeah, question?
Is that something like Parsever approach? You have cross-attention to just a fixed number of tokens?
Sorry, say that again. Is that?
Parsever. Parsever. Google has a paper Parsever.
Oh, I'm sure. Yeah, there's also a T5 sentence encoder. There's a whole bunch of different approaches that do this. Right. Yeah, absolutely. And there's different flavors to this. And of course, there's one assumption that what if this text is like super, super long and take the entire Bible, right? And just encode it in 5 tokens, but it's not going to work, right? So there's some assumption how long this is, right? It can't be too long. But once we've got this, right, you can actually just take noise, denoise it over and over again. Now we have some, noise-free version of this latent feature, and we can just decompress it. I can show you some here examples. So here's actually rock stories. It's like 5-sentence stories. And this here is generated by the diffusion model. So Fred had always wanted to learn how to play tennis. He decided to start taking tennis lessons and so on, right? So, it works very well, right? And the nice thing about diffusion models is, of course, we can generate text, but we can also actually control it, right? So we can actually now take this classifier, for example, and say we want this to be in a certain topic. For example, we have a classifier that says this is science, technology, or this is business, or sports. And if you apply this classifier, we can steer this. And it's much easier to steer than an autoregressive model, right? Autoregressive model is kind of awkward to steer, right? Whereas here, because we're doing the whole text in one go, we can just, use this diffusion, to have this classifier and say at the end, the whole thing should be a business article or should be a science technology article. Okay, good. So that's the first thing on diffusion models. The second thing is, we can actually use diffusion models to generate text. Can we use it to control autoregressive models? And here's a quick quiz to the audience. Here's an elephant, right? And people who have elephants, right? The one problem with elephants is that they're very strong, right? It's good, but it's also a problem, right? Because they can just run away at any given time, right? And if you're a little human, you can't hold them on a leash, right? So what people do is they stick them, tie them to a little stick, and the little stick they put in the ground. Now, why? This is my question to you. Why does the elephant not pull the stick out or just run off? And it could easily, this is an elephant, right? Like, it could just easily pull out that stick. Why doesn't it do it? Yeah.
It's because you do it when they're young. So
That's right. That's exactly right. That's exactly right. So the answer is, when an elephant is a little kid, little baby, right? You do this already, right? You put them, you tie them to a stick, and the elephant, tries a couple times to pull out the stick, right? And can't do it because it's a little baby, right? And so once it's learned, there's no point, right? I have no chance. Then it never tries it again, right? And so at some point it becomes huge, and you just have to put in that little stick in the ground, right? And the elephant knows that basically it can't pull out the stick and it won't do it, right? So that's how people park elephants, I guess. By the way, this was generated by Gemini. So, okay, so we're going to do the same thing. Right? We want to control a language model that's much, much larger than us with a tiny little diffusion model, right? And so how can we control a language model with a diffusion model? Well, when it grows up, right, we learn it, we teach it that it should listen to the diffusion model. That's the trick. So here's how this works. Again, our big model is GPT-2, but I'm sure this whole thing transfers to larger models. So we have this diffusion model, GPT-2, and it's trained on, you put in a prefix and you try to continue it. The old clock on the wall ticked, and then the continuation is loudly as there and blah, blah, blah. And so, you know how this works. The teacher forced it. So what we're doing is we're fine-tuning this model, but we need the stick, right, to tie it to. And this is what we do. We take the actual ground truth of how it's supposed to be continued, right? And we embed it, with an encoder in a fixed size latent, and we stick that into GPT-2. Right? Initially, GPT-2 doesn't know what to do with this, right? But if we just fine-tune it a little bit, right, it will learn that whenever I ask it to continue a prefix, the exact answer is actually encoded in this latent code, right? So I'm basically cheating, right? I'm telling it what the answer is. It's right here, right? Just in this continuous space. Like these numbers here contain exactly this continuation, right? And it's supposed to come up with it, right? So the model learns to basically just, decode this latent code into this text, right? And while I'm doing this, I'm doing one more thing. I'm adding a different amount of noise every time, and I tell it how much noise it is, right? And so the idea is basically, if I have a lot of noise, then it learns, just don't trust this. This is very noisy. And if it's very little noise, then it will just decode this out blank and just write it here. Okay, that's the idea. Make sense? And why is this so cool? Because now what we can do is we can actually generate during inference time, we can generate this latent after it's been fine-tuned with a denoising diffusion model. We can just, we have some initial prefix. This time we don't know what the output is, but the continuation is supposed to be, because now we're at inference time. But what we're doing is we take a diffusion model to generate a latent that is basically a semantic proposal. Like, how should this continue? We generate a continuation here in this latent code, and we stick it into GPT-2. And if we tell it this is zero noise, then it will just decode this as the continuation. If we tell it there's a little bit of noise, it will basically just rely on this a little bit, but actually also use its own brain to kind of do the continuation. Does that make sense? So we basically feed it. We trained it that this is always the answer, and now doing inference time, we basically generate this with a diffusion model. Why is this a good idea? Yeah.
Why does it have to be a diffusion model? Why not be some other text encoder?
Why does it have to be a diffusion model? And the answer is because we want to guide it. Right? So diffusion models is really, really easy to guide. Right? We can actually use a classifier that says this should be toxic or should be not toxic, should have positive sentiment, and so on. And there's also actually classifier-free guidance that works really well with diffusion models. So diffusion models have amazing control. You can control it really, really well. So we can use the control of the diffusion model to kind of roughly get here what we want to say, and then let the GPT-2 model to actually spill it out in text.
How complex are these classifiers?
Oh, just logistic regression. Yeah. The question was, how complex are these classifiers? Super easy, right? You just need a couple hundred examples, right? That's the beauty of it, right? And also the nice thing is, once this is trained, you come up with another, you want something totally different, right? I want, I don't know, something that rhymes or something. You have a classifier, right? And you stick that in, right? And you don't have to retrain anything, right? That's the beauty. Okay. We now do this. Let's say we make it toxic, then it says relentlessly really goes on my nerves, and so on, right? And we can change this. So here's prefix, cycle published by the CTC is running, and if you make it positive, it says 10th edition is getting better every time. That's great, right? And if you say negative, news section in quotes, no substance at all, zero interest, it becomes really, really negative, right? So we can control what the language model is going to say, right, with this little trick, right? And we just need a classifier that's positive or negative, right? And this was just during fine-tuning. So you can do this with any language model, right? It's just a very, very small trick. Here's basically, it shows, how we can, it's a trade-off between toxicity and perplexity, but, you basically have a very favorable curve here. Anyway, let me not go into details. Last part of this talk, just 3 more slides. This is actually a project, again, something that's not published yet, not even archived yet. We just did it submitted to Colm. It's called Stop-think-autoregress. And this is actually based on Luke talked about transfusion, his paper on transfusion 2 days ago. We basically, when we saw this paper, we realized, this is actually really related to what we are doing, right? So, he basically, there's a transformer and diffusion. That's kind of his idea. So here's what we built, and I only have this one slide that can explain the algorithm. This here is doing inference, but it's really, really cool. So I'm just going to explain it to you on a high level. You basically have a transformer that, generates text, right? The, old, and then you stick an old, clock ticked, and so on, right? And now I want to do a continuation. Let's say I want to solve some problem or something. What I do at this point, like the problem basically is that transformers can't think, right? They can only spill out tokens, right? Like thinking is the same thing as speaking, right? For language models, which is weird, right? I mean, if you know some humans, we all know these people who just always talk when they're thinking. That's very annoying, right? So what we would like them to do is actually to think, quietly, right? The other thing is what we would like them to do is think in the latent space, right? Like the token space is really lame, right? Like you take this distribution of the, each latent token is a distribution over 10,000 of tokens, right? And you collapse it into one token when you generate a token, right? So you're kind of really reducing all this knowledge, right? Like also what I just showed you is that we could compress whole paragraphs of text into a bunch of few latent vectors, right? So these latent vectors are way more powerful than tokens, right? So what we are basically doing is saying, okay, you generate some text, and then suddenly you start thinking. And when you start thinking, you basically just have a few latent tokens. And we just start with noise. And we basically just pass them through the network that actually the same autoencoder actually also does the same transformer also does the denoising. So that's the, but this is from Luke's group in UW. So we basically take a bunch of latent codes, we denoise them, we add noise back in, denoise them, and so on. We keep going around. And so basically, we give the language model a chance to learn its own latent code, right, inside, right, to think. Until it, let's say we do a few hundred iterations or something, it thinks. Then it basically has a few latent codes, right? And then we output, then we continue our speaking. And we basically attend over all these latent codes that we very, very carefully selected to essentially solve the problem that we're trying to do. I'm not going to go into how to train this, but it's easy. And so if you now compare this, our model, if we do this thinking, stop-think-autoregress star, we basically have the same quality, this is LLM as a judge, as models that are way, way, way bigger, right? 12 times as big, right? And here, across, coherence, plausibility, reasoning, and quality, and so on, right? So, and the trick basically is that if you do this diffusion, right, you can basically, it's just in the latent space, it's just so much more powerful than babbling all the time, right? So again, future of transformers. I think the future of transformers is to leverage the latent space much better, right, instead of constantly babbling. Some more slides that show if you do more diffusion, it gets better, and I'm trying to finish on time. So. This is the conclusion of the second part. So in summary, diffusion models are awesome because they're easy to control, and we can actually put in diffusion into our language models in the latent space. And doing this, we can do a whole bunch of really cool things. Number one is we can generate new text. That was the first part of the diffusion thing. We can also guide the language model if we wanted to, for example, be semantic positive, or because diffusion models are really easy to guide. And we can also, and that's the last part, we can also make it think in the latent space, right, which is extremely powerful. And I want to thank my students who are right now partying in Puerto Rico. And in particular, actually, Justin Lovelace, and this is actually these are colleagues of mine, Jennifer and Yoav, and in particular, Justin Lovelace, who was the brains behind all of the diffusion model work. Thank you.
I think we have time for so.
Yeah, thanks for a great talk. So for reasoning in latent space, so I agree that you can track all the hypotheses or reasoning paths simultaneously. But do you think it's also much harder to learn compared to reasoning language, where you get the prior from a language model?
Yeah, good. So the question basically is, yes, the one thing you can do if you reason in latent space, in some sense, you have a distribution over tokens, so you can actually think about many different chain of thoughts at the same time. But it's very hard to get signal for this, right? And so what we're doing here in this case, we actually, during the training, we do the same trick that we did with, the elephant trick, basically. We basically took in this case, it was basically trained on continuations, and we basically feed the latent code, the continuation during training time, so that the autoregressor basically learns, how to listen to it, and then it's the same cheating trick, basically, essentially. And then during diffusion, basically, during inference, it's basically just the noise. So here we just use the continuation that we have. So we assume basically during training time we actually have some continuation about the reasoning. Does that make sense? Yeah.
I don't need a mic. Yeah. So it seems like your talks are kind of similar in a way. In both talks you put knowledge into LLM. And my question was, were you thinking of using something as a time-sensitive knowledge? Because like the previous talk, the facts can change. Like you were talking about birth date, but it could be like a quarterly report date that you might put in. And here you also put knowledge in the model, which also can be time-sensitive. That can change. And LLMs have a problem with renewing the knowledge.
Right. So I guess the question is about fact changing, right? So what if you have some facts that change over time? Yes. In the first part, we believe, although we haven't tested it yet, that we can change the facts very easily in the database. And the second thing is more style changes, actually. Like it's less about facts. Like the fusion models, here the idea is more like, we want to, not to be offensive, or not to or
so it wouldn't work for facts?
It works less for facts. It works when you have classifiers. So you basically need some, where's my, here are these classifiers, right? You basically need something that, it works great if you can train a classifier and say, I want this and not this type of language, right? So for example, language that's safe for kids, right? You could say, I'll have a language model, I have the same language model every time, right? But when I have a user that's under 16, right, I apply the classifier that says kids safety language, right? And when it's an adult, then I don't apply that classifier, right? But that would be the use case. Yeah. Actually, I think you should use the microphone because it's live stream. Yeah.
Yeah. When I think about diffusion models, the first thing that comes to mind is efficiency. Like they don't need long compute like what we do with transformers, right? They're computationally efficient, much more efficient diffusion models. And your talk touches more on the controllability side of things, and the diffusion work that's happening in text, that's really happening because it's efficient.
So there's actually there's a different parallel line of work. By other people, it's discrete diffusion. So discrete diffusion, right. You don't do the diffusion in the latent space. You do the diffusion right on the you mask out basically tokens. And then you're right. These models are way more efficient.
Right.
Because you basically generate the whole text in one go. A bunch of forward passes, right? And you're not doing it autoregressively. So, people claim it's about 10 times faster. This is not what we are doing, right? So we are in the latent space, right? So it's a different, we don't have that benefit.
And
right?
do you think we can combine both these?
Yeah, can you combine them? You probably could. I mean, we haven't looked into this. I mean, the decoder could be a discrete diffusion decoder, right? Yeah. Why not?
Yeah.
We'll take one more question and have a break.
Thank you. I'm just curious about these classifiers. So do you train this T5 model yourself, or you just take pre-trained T5, turn it into your denoising transformer?
Yeah, so this is actually, the T5 sentence encoder was just pre-trained.
So then you rely on the fact that T5 encodes all of these things that you want to control for eventually, right?
Yeah, all T5 sentence encoders is just an autoencoder. So basically, you can encode a sentence and then you can decode it again.
I mean, let's say you want to control, you made this example, child-safe language, right? You assume that there is a direction in T5 that encodes that, right?
Yeah, but there is, right? Because you can decode it again,
yeah,
right?
But now let's say I want to control for something that T5 doesn't have, right? Then do I need
then you would have to. Okay. So if your data is totally different, let's say you suddenly have, a different language, like it's Mandarin or something, right? You would need to have a new autoencoder, but that's easy to train, right? Because you just need text and you just train an encoder and decoder. In fact, initially we started to have our own autoencoder, and then we just realized that it's much easier to take one that's off the shelf. Just simplifies things.
Thanks.
And so the classifier is very easy to train, right? You just need some examples, positive or negative.
Yeah, we ran out of time. Thanks, Kilian, for the talk, and let's come back in 30 minutes.
Thank you.